sick. She's on antibiotics. So
might just be you too. Good. Okay. Hope she feels better. Okay. Yep. So today's theme or topic is condensed matter, and we're gonna we have some questions for our panelists, but please feel free to pipe in and ask anything you want. I know some of you do work in condensed matter labs, so you probably know more than others, but I'm in astronomy and I don't even know what the term means. So we're gonna talk about that, and we'd like to thank our panelist, Dr. Nadelson, and I'm gonna say his first name, Dr. Andre, so for being here and donating their lunch hour. So let's go ahead and get started.
Yeah, I'd like to thank all of you for coming and our panel members for the participation. First of all, let's just do short introductions. If you can talk a little bit about what kind of research you do and what kind of
Go ahead. So my name is Andriy Nevedomsky. That was the trouble was the last name we had. So I come from Ukraine, and that explains my name. I did my PhD in Cambridge University in England, and then before coming to Rice, I did a postdoc terms in Canada and in New Jersey at Rutgers University before coming here. So my field is theoretical condensed matter, meaning I don't actually do any experiments, even though I always love to, but I don't think I'm any good at that. That means that from my perspective, condensed matter is a series of beautiful mathematical expressions that you can try and capture the reality with. And so my research focuses on trying to understand the properties of real materials, and by real I mean something that one can study. And often the kind of questions one poses is, let's say experimentalists have measured a certain property, they're not quite sure what it means or what the physical meaning of a certain peak in the spectrum is, and one can try to understand that. And some of the problems are more fundamental than the other. But overall, I guess the kind of the significant line that goes through my research is trying to bring together the experimental research and the theory. So in some people call it the Bell Labs style of physics, meaning if there is no experiment, there is no problem. Now this is very different from string theory, where there is no experiment, there is a big problem. So I don't know how relevant this is, let's say, to astrophysics, right? There is from what I understand, and again here I'm speaking out of my depths, the discovery of the cosmic background radiation has put the field of cosmology and astrophysics on a much firmer basis than what it was before, by providing at least something to make a cross-check against. So condensed matter is different in the sense that there are many cross-checks you can make, and often the conditions are more stringent than you want. Sometimes experiments almost contradict each other.
Okay. I'm Doug Nadelson. I've been here about 10 years, a little 10 and a half years now. And before I was here, I did a postdoc at Bell Labs, and before that, I did a doctorate at Stanford doing low temperature physics. So I was really a low temperature condensed matter experimentalist, and now I'm definitely more of a nano condensed matter experimentalist. Being an experimentalist and being a faculty member means your students do all the hard stuff, and, except for the fundraising. No, it's not quite true. I mean, condensed matter is it tends to be a very experimentally driven discipline. I mean, physics overall is an experimental discipline, string theory aside. But condensed matter is particularly experimentally driven discipline. The kind of stuff that's going on in my, I guess the common thread that runs through my group's work overall is when you take, so condensed matter physics is in some sense a melding of quantum mechanics on the one hand and statistical physics on the other. Generally, we're interested in problems that involve very, very large numbers of particles, and obviously you can't solve the Schrodinger equation for a system that contains 100 million electrons and 100 million ionic nuclei. You just can't do it. There's no practical way to do that. So there are statistical ways of dealing with some of these issues. Condensed matter is the study of systems that are well described by this. And when you take like a solid-state physics class, you learn an awful lot about, one of the favorite, as you've all realized, physicists are fundamentally lazy people, right? And we want to do the simplest possible problem, as long as it's not so simple that it's not true anymore. And very often people like to say, well, let's have an we've got a crystal. Let's assume the crystal's infinitely big and perfectly periodic, and that makes the math simple in certain ways, simpler in certain ways. The thread that runs through my research is looking, as a nano sort of person, looking at, on the one hand, when some of those nice approximations break down because of finite size effects, or what happens when there are a lot of interesting length scales that come up when you talk about when you talk about condensed matter systems, and particularly if you drive them out of equilibrium in some way. There's a whole bunch of different length scales that are important to the problem, and now we have ways of making things comparable in size to those length scales. So you really get to see how do the big approximations fail. And the other thread that runs through this, I guess you could say, is that there are certain things that we like to neglect. You can get very, very far in condensed matter physics ignoring the fact that electrons repel each other, or ignoring, so that's sort of the whole single particle band structure picture. Or you can get pretty far ignoring the fact that the ions can never move, right? This is sort of the Jahn-Teller, the Born-Oppenheimer, Born-Oppenheimer approximation, where you assume the nuclei just sit there and the electrons do their thing. And again, it's very interesting to look at systems where this stuff doesn't work. So that's kind of the thread that runs through my stuff.
Okay, well, thank you very much. The question that we came up with is, obviously, the things you're currently working on, you love them to death and everything. But what the question is, what is hot right now in condensed matter?
What is hot? Well, I can tell you a couple of things that are very fashionable. I'm sure you could do the same. I mean, some of the things that are most fashionable right now, anything to do with graphene. We won a Nobel Prize in physics this past year. Perhaps a bit early in my opinion, but it's still a very interesting physical system. So graphene as a subject of study is very hot, in part because it's structurally, the idealized version of graphene is so simple that you can readily get an undergraduate to do a band structure calculation that's quite good. And so when the theory is that accessible and the system can be easily gotten to in the lab, there's a lot of enthusiasm for it. And it has interesting physical properties. And I guess topological insulators are another area that are very hot. So it turns out that it still amazes me. The band theory of solids was developed in the 20s and 30s. And for sort of 70 years, people just thought that insulators are insulators, right? You can have the simplest way to have an insulator is you've got some filled electronic states, you've got a region of energy where there's no allowed electronic states, and then you've got empty electronic states up here. And if that gap in the band, between the bands is big, like several electron volts, then you have an insulator. And it wasn't until 2005, maybe? Is that a fair statement? That Meillet and Kane, so basically people had the realization that not all band insulators are the same. There's actually two kinds. There's the boring kind, and then there's the interesting kind. The interesting kind are called topological insulators, and they have properties which I would be stretching myself to explain extemporaneously. But one feature of topological insulators is that they have states that live at their surface that are special and are, because of deep mathematical reasons, these states are very, very robust. So if you crud up a semiconductor, the ability to push charge through it goes down because basically the disorder, in some sense, the perturbation to the potential of the electron's field due to disorder is big and it matters. And it's pretty clear that in some of these topological systems, there's reason to believe that that kind of disorder doesn't really hurt you. You can have states that have interesting properties that live for very, very long times, even if you've got dirt lying around. What other things are hot?
Well,
Nick time.
Well, yes, I was going to say that. So there is a big symposium which goes every year in condensed matter physics, which happens every March. Now, if the March meeting is anything to go by, you look at the number of sections, and you look at what, because usually it means that there are lots. If there are lots of sections on a certain topic, and lots of parallel talks, that means there are lots of people working on the subject. and typically that means that it's hot in one way or the other. So iron-pnictides are the compounds that have been discovered in 2008. And they soon gained a lot of popularity because it was the second known example of what we usually refer to as high temperature superconductors. Now, high doesn't mean room temperature, at least not yet, but they carry a lot of promise in the sense that they're moldable, they're easily, metallurgically, they're easy to grow. If only one could make the temperature, let's say 10 degrees Kelvin higher, which seems not that terribly out of bounds, then they could be cooled down to liquid nitrogen temperature, which again technologically would be important. Now, from the physicist, from the fundamental science point of view, what's so interesting about them are two things. One is that the high temperature suggests that the mechanism could be unconventional, and B, maybe that would explain the other infamous kind of superconductivity that has been known for 25 years in the context of the cuprates. So the cuprates won the Nobel Prize, actually I forgot when, 87 or 88?
So
basically a year after the discovery. They were discovered in the 86 by two Bellab's physicists, if I recall correctly, Bernardson and Muller, who in the class of ceramics. And till this day, there are debates going on as to what the mechanism for superconductivity is. Now, up to 2008, when these new materials came up, people kind of were giving up on that, saying that it's very complicated, and there is this, and there is that, and you'll never probably be able to understand it.
I would even go further. There's a certain senior theorist who you and I both know, but I won't embarrass him by naming names, who was going around giving colloquia around the country, not here, going around giving colloquia around the country, talking about how copper is special, basically. Like that the whole secret to the cuprates is the copper. And that without that, basically, you know, the cuprates are the best there's ever going to be because copper is special. And then, you know, 2 or 3 years later, voila, another whole class of high temperature superconductors that don't even have copper. And so this was, you know, I mean, people got very excited because a lot of people were worried that, like, well, the cuprates really are all there is. And you know, people have been working on it for 20 years, and that's the end of the story. And they're so complicated, they're hard to understand. But now that there's a whole second, you know, it gives you hope that, in fact, the high temperature superconductivity may be a much more generic thing than was otherwise thought.